Okay, let's do some applications of exponentials and logs, some nice word problems. For exponentials, one of our most popular is a population problem. So say we're given that the number of bacteria in some jar or petri dish or something, some population as a function of time is some initial amount times some exponential function, where k here is sometimes called the growth factor or the growth rate. So our speed of growth is buried up here in k, and our p here is just our initial amount. So say, for example, we start with 1,200 bacteria, and they grow at some rate like this, where t is in, say, hours, and p is number of bacteria. Okay, some population. We're counting how many we have. So I might ask a question like, well, how many bacteria are there after 5 hours? So we got to ask ourselves, am I giving you the time? We would plug in, or am I giving you the population? And here I'm giving you the time. So we would just plug in. P of 5 would be 1,200 e to the 0.3 times 5. And then we just get out our trusty calculator and plug that in. And we get, plugging that in the calculator, 5,378.03 bacteria. And you're wondering, wait a minute, can you have 0.03 bacteria? Yeah, you can. Bacteria are always in the state of reproduction. They've always some fraction of the way through reproducing. So I've got one that's 0.03 of the way through dividing again. Okay, so after 5 hours, that's how many we would have. Okay, what if I wanted to know how long it takes until we get double the initial amount? So find the doubling time. So I want to know how long it takes until I get double the initial amount. Well, I started with 1,200, so I want to now solve for the time. So I want double the initial amount, and I'm trying to solve this for time. Hey, that's an exponential equation. It's a good thing we know how to solve exponential equations. So I could divide through by the 1,200 here. Of course, on this side we get 2 equals e to the 0.3t. We take the natural log of both sides. So we'll get natural log of 2 equals natural log of e to the 0.3t. On the right side, natural log of e to the anything, those are just inverse functions. They just cancel out. So I get natural log of 2 equals 0.3t. And so t equals natural log of 2 divided by 0.3. And that's, well, doubling time is always going to be that. It's always natural log of 2 divided by this k value. Doesn't matter how many you started with, because you're trying to end up with double what you started with. And so we could throw that in our fancy calculator and get about 2.31 hours. Takes a little over 2 hours to double the number of bacteria in this particular dish. Okay, radioactive decay problems. These are honestly just exponential decay problems. They're just like population growth problems, only now we'll have decay instead of growth. So our basic format is we'll have some amount after time t is some initial amount, e to the kt. Only now we'll have a negative k value, a negative growth factor which is what gives us decay. So say we have some material and we start with 500 milligrams of it, and say it follows that's at 0.8 e to the negative 0.8 t, where let's say t is in years and a is in milligrams. Okay, let's say if we wanted to know how much we have after 8 hours, that's pretty easy. We just plug in 8. The typical kind of problem that causes trouble here is finding the half-life. That's when you have half of however much you started with. So I'm looking for the time here. I'm not plugging in a half. I'm not saying it's been half a year. I want to know how long it takes for this to decay, so I only get half of what I started with. Well, right now I have 500, so half of that would be 250. And I'm solving now this exponential equation. This is a lot like the last problem. Divide over the 500. 250 over 500 is a half, so that's how much I want. I want half of what I started with. I'm going to take the natural log of both sides. Natural log of e to the anything is just that thing, because those are inverses, they cancel out. And then divide by that negative 0.8. I get t is natural log of a half, natural log of 0.5, divided by negative 0.8. So if you'd rather think 0.5, natural log of 0.5 divided by negative 0.8. And you may be thinking, wait, whoa, we're getting a negative time. No, we're not. Throw that in your calculator. Natural log of 0.5 is a negative number. The answer is positive. So we throw that in our calculator, and we get about 0.867 years. T, of course, measured in years. Okay. Our next kind of problem are interest problems. Compound interest. So our formula for compound interest is the amount of money you have after some time is P times 1 plus R over N raised to the NT. P here is your principal. It's the amount of money you began with. Time's always measured in years. N is the number of times you're compounding per year. And R is your annual percentage rate as a decimal. So the main key here are all the different N's. If we're compounding yearly, then N is once per year. If we're compounding monthly, we compound 12 times per year. If we compound quarterly, that's 4 times per year, and daily is 365 times per year. So our typical problem will look like Dave invests $7,000 at 4.5% APR, compounded quarterly for 11 years. So we identify all of our variables. My principal was $7,000. My interest rate as a decimal is 0.045. Turn 4.5% into a decimal. Compounding quarterly, so N is 4, and I have 11 years. So my amount after 11 years is 7,000. 1 plus R, 0.045 over N raised to the NT. 4 times 11. You really, right now, should pull out your fancy graphic calculator and type this in. Make sure you know how to type this in. This is where mistakes happen, right here. This exponent needs to be in parentheses. So you would want to type 7,000 parentheses 1 plus 0.045 divided by 4, close your parentheses, your exponent button, the caret, 4 times 11, close the parentheses, and then hit enter. If you don't type it just like this, you are going to get the wrong answer. All right, so let me plug this in a calculator. And I got, like magic there, $11,451.79. That's how much money Dave has after 11 years. That is money. We do want to round that to the second decimal place. Make sure we have our dollar sign. Okay. Continuous compounding. It's just like regular compounding, only now the idea is we want to think we let n go to infinity. We are compounding every single mathematical instant. Every instant the bank is putting more money into our account. And our formula is A equals the PERT formula, P times E raised to the RT. There's no n in the formula because n is literally infinity. So let's say we have Dave again. Same example as before. We have $7,000 to invest at 4.5%, so 0.045. And let's say our time is still 11 years. I don't have an n here because n is infinity. So I would plug in. The amount I would have after 11 years is 7,000. E raised to the RT, 0.045 times 11. Again, make sure you type this into your calculator, right? That's 7,000. You have an E to the X button on your calculator. When you type that, that types out E and opens up a parenthesis. That will happen on its own. We type 0.045 times 11, and then you got to type the close parenthesis, and then enter. Okay, let me plug that in my calculator. And I got $11,483.50. Now, you'll recall, if we were compounding quarterly, we got 11,451. So, in the first scenario, I compounded only 4 times per year. In the second, I compounded not once per second, faster than that. Faster than 1 billion times per second. Every mathematical instant, my money is continuously growing. And after 11 years, the difference is about $30. Compound interest is kind of a scam. What matters is not how often they compound. What matters is the interest rate. The interest rate makes more of a difference than any number of compounding. Okay, now let's do a logarithm word problem application. The most common one is the decibel level, the decibel scale. We hear all the time how loud something is. We measure that in decibels. And our formula for a decibel level is 10 times the common log. Notice there's no base here. This is log base 10 of some intensity divided by some reference intensity and measured in decibels. This reference intensity, I0, I0, is 10 to the negative 12th watts per square meter. This is about the threshold of human hearing. That's like 0 decibels is the tiniest sound that we can hear as humans. Okay, a whisper has an intensity about 1,000 times that. This number is about 1,000 times bigger than this one. We want to figure out its decibel level. Okay, so we just plug in this I value here. We'll get our decibel level equals 10 log of 10 to the negative 9th over 10 to the negative 12th. Okay, we'll clean up our exponents here. 10 to the negative 9th divided by 10 to the negative 12th is 10 to the 3rd. Common log, that's log base 10 of 10 to the 3rd is just 3, so we get 30 decibels. A whisper has a decibel level of about 30 decibels. What about an everyday conversation? You're talking to someone about the volume I'm talking right now. That's about 1,000 whispers. This number, this intensity, is 1,000 times a whisper. So let's figure out what decibel level I'm talking at right now. So it would take 1,000 people whispering to be as loud as I'm talking. So do you think my decibel level is going to be 30,000 decibels? Is it going to be 1,000 times this? Let's check. Our decibel level will be 10. Common log, log base 10, of my intensity divided by I0, 10 to the negative 12th. It's just rules of exponents there. 10 to the negative 6 divided by 10 to the negative 12th is 10 to the positive 6th. Log base 10 of 10 to the 6th is just 6. So I'm talking at about 60 decibels now. So I'm 1,000 times louder than a whisper, but that's only 30 decibels louder. Every increase in 10 times the intensity is 10 extra decibels. That's why we're using a logarithmic scale here. So an increase of 10 decibels is 10 times more intense. So say going from 100 to 110 decibels, that would be 10 times as intense. Okay, right now should be popping up some additional videos related to exponentials and logs. Click on those for more.